Second day morning. First of all, I want to thank the organizers for this great workshop they put together, and also giving me this honor to present our first speaker, David Ruelle from IHES or IHES. Several of us at one point or another have learned of the DLR condition, the R of DLR. But he's quite well recognized, and he's won basically every award in mathematical physics and theoretical physics, including the Boltzmann Medal, Henry Poincaré Prize, and several others. It's my honor and pleasure to introduce David Ruelle. He's going to talk about zeros for partition functions and graph polynomials. Please.
Thank you. I'm quite honored to be invited to this place, and I will talk about the Lie-Yang circle theorem. The Lie-Yang circle theorem was discovered experimentally by Li and Yang, and since they are good mathematicians, besides being good physicists, they found a proof. But the proof was not easy. And then various people like Mark Katz and Feynman tried to improve this, and they managed to some extent, but not a lot. And then there was this young Japanese person who found a really simple proof. So this is the reference to Lie-Yang, and I made an extension of the lemma, which is central to the work of Asano, and I shall talk about that. So here is the lemma. So if you get something out of this lecture, this would be this lemma. So assume that you have a bi-affine polynomial a plus bz1 plus cz2 plus dz1, z2, where the coefficients are complex numbers and z1, z2 are complex variables. This is separately affine in z1 and z2, and assume that this function of z1, z2 does not vanish if z1 is outside of a set k1 and z2 outside of a set k2, where k1 and k2 are compact, are closed subsets of the real of the complex plane, and do not contain the origin. Then the statement of the lemma is that the affine function a plus dz, where you forget the terms in b and c, a plus dz does not vanish if z is outside of the set minus k1 times k2. k1 times k2 is the product of an element of k1 and an element of k2. So passing from this bi-affine function phi to this affine function phi tilde is called Asano contraction. So let's consider the example which was considered by Asano himself. If this polynomial does not vanish when z1 and z2 in absolute value are less than 1, then the function phi tilde does not vanish if z is less than 1. That's easy to prove. And the proof was given yesterday. In fact, if this function does not vanish when z1 and z2 are inside of the unit circle, then the function a plus bz plus cz plus dz squared does not vanish, and the roots of this polynomial of second degree have a product which is minus a over d, and therefore one obtains this result. The case where the set K1 and K2 are somewhat bigger or different has to be handled separately, but you can imagine that this is not a very difficult problem. In fact, I found this result, and then there was a simplified proof by Freeman Dyson, which is the one that is printed in my paper. Okay, now Liang circle theorem. Suppose I have, I denote by n between square brackets the set 1, 2, etc. n, and I consider variables z1, z2, zn, and I shall write z to the power x, where x is a subset of 1 till n, as the product of the x of the zj, where j belongs to x. Then if you have numbers a, j, k, which are real numbers between -1 and 1, consider the polynomial in n variables, which is the sum of the z to the x of product for j in x and k, not in x, of the a, j, k. Then the claim is that this polynomial does not vanish if all the z's are less than 1 in absolute value. Now, the proof, I'll say what the proof is, and you will have to think a little bit to check that this is really a proof. I consider the trinomials zj, zk plus ajk, zj plus gk plus 1, where I have not mentioned the variables at the top. And if I take the product of all these trinomials and make an Asano contraction of all variables which have the same name, then I get this polynomial. Now, Asano contraction, if you have polynomials that do not vanish inside of the unit circle, produce something that again does not vanish inside of the unit circle. So that gives the proof of the Lie of this result. Now, the Lie circle theorem corresponds to the situation where I take all the zj's equal to some variable z. So it's a polynomial of degree n in one variable instead of a polynomial of degree 1 in n variables, and you find that this result implies that the polynomial of degree n in one variable does not vanish inside of the unit circle. By some symmetry of z going to 1 over z, this does not vanish outside of the unit circle either. So it can vanish only on the unit circle. So that is the Lie circle theorem, and modulo the fact that you have to make sense of this little proof, this is a very simple result, contrary to the original proof of Lie and Yang. So that's the corollary, which is the Lie circle theorem. Now, consider multi-affine complex polynomials which are such that they have this form, and corresponding to a polynomial, to a multi-affine polynomial psi, I define also a psi dagger, which is obtained by changing the variables, replacing those which are in k by in x by those which are outside of x, and taking the complex conjugate. So we say that psi is a Lie polynomial if when this thing is less, when z1, zn are less than 1, psi of z1 to zn is different from 0, and the psi dagger is also different from 0. So this is a natural definition in view of the Lie circle theorem. Incidentally, the fact that I look at multi-affine polynomials instead in n variables instead of polynomials of degree n in one variable, this was introduced already in the original proof of Lie and Yang. So what they proved is the preliminary theorem that I described.
Question. Isn't the second polynomial just the first one where you, after you divide by the product of all the z's?
You must speak. I mean,
Okay, never mind. We'll talk later. Right. So I'm just asking you if the second polynomial is the same thing as the first polynomial. This, after dividing by the product of all the z's and then taking complex conjugation.
Yeah.
So is it a new? It's a separate condition? No.
Okay.
That's it's not important. No.
Okay. So I mean, not necessarily. I mean, you are probably right that this is not this is the same condition up to dividing by
Well, okay. Yeah.
something that may vanish. Okay, so since these multi-affine polynomials are naturally associated with the Liang circle theorem, forget about what is on screen. My problem, one problem that I asked myself, and which was discussed in fact yesterday, is the following. Can one generalize the Liang circle theorem, which is a theorem which involves coefficients A, J, K, to more general interactions where n-body interactions appear. So I did not describe the physics of this thing, but the polynomial that occur in the Liang circle theorem is associated with, it's the partition function of a spin system in which you have a spin which can have values 0 or 1, and the case dealt with by Li and Yang is a case of pair interactions. Now, can one deal with n-body interactions instead of pair interactions? And the result which one obtains is that one cannot, if one imposes the Li-Yang condition, essentially the zeros are on the unit circle, for all values of the temperature. So there's no generalization of the Li-Yang circle theorem which holds for all non-pair interactions and all temperatures. However, as explained yesterday, there are generalizations if one excludes a part of the temperature range. So that was the talk given yesterday. So the formal statement is this. What it says essentially is that if you have the Li-Yang condition at high temperature, then you have the Li-Yang condition at all temperatures. So it may fail at high temperature if you have non-pair interactions, but not otherwise. So if you have a Li-Yang polynomial phi beta for a sequence of betas tending by positive values to 0, then you have that it's a Li-Yang polynomial for all values of beta. And furthermore, there exist real numbers w, j, k, aj, and complex b's such that wjk is equal to wkj, and the w which occurs in this formula. So the w are essentially the logarithm of the coefficients of this multi-affine polynomial. They must have this form, which says in effect that you have pair interaction, and in fact ferromagnetic pair interactions, because you have this condition that the w jk are symmetric and have a positive value. So that is the generalization of Liang.
That agent not required to be positive or agent.
I beg your pardon?
Agent, that not required to be non-negative, or we require that to be non-negative.
A sub j. No.
A
Subject. Do we require that to be
Oh,
non-negative or?
these coefficients are non-negative, or let's say, well, let's say they are finite. So could they be
Because the I is
zero? I mean, no, we say they must be exponentials of something which is finite, so they cannot be zero. As stated. Okay, so that's all I find, but this is all based on the Asano form of this lemma, and the generalization which I produced, which is that the sets K are not necessarily the outside of the unit circle. Does this bring something useful to physics? And the fact is that there are, it allows one to deal with some polynomials in multi-affine polynomials, which are graph counting polynomials. So a graph is what I call a graph is a finite graph, undirected, and where there may be multiple edges between the vertices. And I associate variables with the edges. So in the previous version, in fact, I associated variables with the vertices. Now I associate variables with the edges. And suppose I have a set of subgraphs. So let F, curly F, be a set of subgraphs. I define a polynomial, which is a graph counting polynomial associated with the set of subgraphs, as the sum over the subgraphs in question of z to the power f, where z to the power f is the product of the variable z e associated with the edges in the subgraph. Now we can obtain in the obvious way a polynomial of degree n in one variable by making all these variables z e equal to a variable z, and this is then the sum over the subgraphs in question of z to the power the number of edges in the subgraph. So this is the subgraph counting polynomial associated with the family of subgraphs. Now, there's one simple family of subgraphs which one can think of, which is the subgraphs such that each, so that the subgraphs, so that two adjacent edges cannot be occupied simultaneously. So these are let me go back to that later. So these are the dimer subgraphs. So the subgraph counting polynomial, which counts dimers, is then simply the sum over dimer subgraphs of z to the power the number of edges occupied by the dimer subgraph. And there is a theorem of Hyman-Lieb which says that the zeros of this polynomial, of such a polynomial, must be real negative. The paper of Hyman-Lieb contains many other results, but in particular this result. And the fact is that it is an easy consequence of the Ruelle, of the Asano-Ruelle lemma. Suppose for each vertex V, I write an affine polynomial, which is 1 plus the sum over E in the in the graph with 1 point, so you make a sum over edges in the graph such that one extremity of the edge is in fact V. So this is because there can be only one edge ending at each point. This is an affine function. Now, the notion is that if you make a product of such affine polynomials over all vertices of the graph, and then make an Asano contraction of the variable z with one end at V and one end at some other point, then you get a multi-affine polynomial which counts the dimer subgraphs. Is that clear? Okay, so the problem now is, can one say something about this multi-affine polynomials? Now, what one will have to do is consider a region such that this affine polynomial does not vanish, and consider the various regions associated with these things. Now, let me draw here's 0, and take some half plane which does not contain 0 but contains the negative numbers. So if this is close to 0 but not quite 0, if you take points which are in this half plane and multiply them by points which are in the same half plane, you get, in fact, the outside of a parabola. It's a fact of the geometry of the complex plane that taking a line and multiplying by itself you get a parabola. And so if you have something which does not vanish in this region, then the contraction of two variables does give something which does not vanish in the inside of this parabola. So there's a little bit of geometry of the complex plane that comes in this, but that's not very hard to prove. Now, I have taken a line, a half plane of this sort. You can modify this half plane, take a different half plane, and what you find is that if you have something, variables which lie on a straight line of variable inclination, you get something which, by Asano contractions, is not 0. So what happens is you have a multi-affine polynomial associated with dimers that does not vanish if all the variables are along a line which turns around this way. And in fact, you must avoid the negative real axis. So, putting all variables equal to a variable z, what you find is that you have a polynomial, the dimer counting polynomial, which does not vanish outside of the negative real axis. So this is a new proof, and perhaps simpler than for the result of Hallman-Lieb. Yeah?
Do you get upper subbounds on the roots from this method, let's say, in the monomer dimer case? Well, because the important thing in Hallman-Lieb was the bound, not just the fact the roots are real, they also provided the bound.
The bound on the domain.
In terms of the degrees, yes.
Well,
This method also gives that bound or not?
Well, it does give a bound in the sense that you have some. You start with a graph which has a finite number of edges ending at each point, and you take the maximum number of edges that can end at a point, and this will give you an estimate of where along the negative real axis can be the roots. Okay, so that's very nice to be able to prove a theorem which has already been proved by someone else. But the idea is you would like to prove something new, and then the new thing that I considered was the case of so that's the Hyman-Lim. The case of unbranched subgraphs. So unbranched subgraphs are subgraphs such that every vertex can be a common point of two edges of the subgraph, but not more than two, 0, 1, or 2. So unbranched subgraphs are topologically either circles or straight lines, straight line intervals. And then the notion is that you can again obtain the subgraph counting polynomial for unbranched subgraphs by Asano contractions with of a product of things which correspond to choosing an individual vertex. And so for each individual vertex you will have a second degree polynomial with something which is a constant term plus a linear term plus a second degree term which corresponds to pairs of edges that can meet at the vertex in question. And then you have to get you have to start with the fact that such polynomials will not vanish in a certain region. Now, it so happens that there is a theorem that says that if you have polynomial which is symmetric in a multi-affine polynomial which is symmetric in its arguments, and if it does not vanish, well, if taking all the arguments equal, you get some region in which, some circular region in which this does not vanish, then it also does not vanish when you take all the variables to be different. So that's a famous theorem, which is Grace's theorem, so-called. And so what one has to do is to look now at second degree polynomials in one variable and of a certain particular form which corresponds to let me you can imagine what it says. It says that at a given point there can be either 0 edge or 1 edge, so that's n z, and or 2 edge, and that is n minus 1 over 2 z squared. And you have to find out when this does not vanish. And it so happens that this polynomial does not vanish in a region which in the complex plane is an edge like this, 45 degrees. So it does not vanish when the things are in this. So if you take any line like this, you will have the possibility to take z in this in one side of this line, and you can turn this line so that it goes this way or this way. So when you do the calculation, which is in fact not hard, what you find is that the subgraph counting polynomial counting unbranched subgraphs in fact does not vanish in the right half plane. So that's a satisfactory result. Can one get something out of this? And the fact is that a number of years after this result was obtained, which at the time was a moral satisfaction, that one could prove something for a class of subgraphs different from the dimer subgraphs, that one finds a result that under rather wide conditions on the original graph, say that it's Zn for finite n, and take the edges joining neighboring points, then and take a subset of that tends to infinity in an appropriate manner, like some big circle, then one obtains the result that the distribution of coefficients of this polynomial is asymptotically Gaussian. The proof is complicated and involves a number of results that I cannot talk about. Many people in this audience probably know these results better than I do. But let me give you an intuitive idea of why this could be true. So take a polynomial which has, take a real polynomial, in fact, with positive coefficients, that does not vanish in the right-hand half-plane. Then you can write this polynomial as a product of either linear polynomials corresponding to a root on the negative real axis, or a pair of complex conjugate numbers which are in the left half-plane, and the corresponding second degree factor which this corresponds to has positive coefficients. Okay. Then assume, and that's a real assumption, but it's a natural idea, that these factors are in fact independently distributed. So the factors of the unbranched counting polynomial is the factors are what are second degree or first degree things with positive coefficients, and suppose these are independently distributed. Then going, to a sum instead of a product, this means that there will be a Gaussian distribution. And that's as far as one can go. But it makes it natural that the condition that the zeros are in the negative real in the negative complex plane. This is natural because if you had a pair of positive with positive real part, then this would give a factor which does not have positive coefficients. Okay, so I'll stop there. Thank you.
Any questions? Philosophical remarks?
May I ask a historical question? So I want to ask a historical question. So have you tried, when you deal with monomer, dimer, all that stuff, have you tried to attack van der Waals conjecture for the permanent?
I don't. You will have to remind me of what.
Okay.
No, I've known it, but I've forgotten it.
Yeah, okay.
Any other questions, comments? Okay, but as usual, we have a break until 10:30, so feel free to approach Dr. Ruelle closer in person and ask any more questions. Thank you again.